Okay, so far in this unit we've seen two types of nuclear reactions. We've talked about radioactive decay and artificial transmutation. And then we've also talked about the concept of binding energy, as well as mass defect, both in the context of a nucleus and in a nuclear reaction. Okay, so to finish up this unit, we're going to talk about the last two types of nuclear reactions, nuclear fission and nuclear fusion. Okay, now it's important that you understand that in all types of nuclear reaction, they all basically operate the same way. You have typically some type of mass defect, which can result in the release of energy as a product. Okay, so typically, not always, but typically you have more mass on the reactant side, on the left side, and then that mass is transformed into energy on the right side. Okay, now, I say typically, I'd say 90% of the time that's true. It's also possible to have nuclear reactions where that is not the case. Those type of nuclear reactions actually require a lot of energy on the reactant side to occur, but that's not super typical. I'll try to do at least one example of that later on. But most of the time you have more mass on the left side that's converted to energy on the right. So let's talk about nuclear fission. Okay, so nuclear fission, when people talk about nuclear power plants or most nuclear bombs, they're talking about nuclear fission. By definition, nuclear fission refers to the splitting of a large nucleus into multiple smaller nuclei. Okay, now typically the way that occurs is you take a neutron, which is usually produced by some other type of nuclear reaction, and you basically shoot neutrons at a heavy nucleus. It has to be a really, really heavy nucleus, like uranium or plutonium. And if the neutron has just the right amount of energy and it's able to hit that unstable nucleus, that nucleus can actually split into two smaller daughter nuclei, and most importantly, additional neutrons. Now, it's those additional neutrons that give nuclear fission their power, no pun intended. Okay, as we'll see in just a second, because those additional neutrons are capable of causing a chain reaction. So you can always spot a fission reaction because you'll see neutrons on both sides of the equation. And plus, just using the definition of fission, you typically have one really, really heavy nucleus on the left side and then two smaller daughter nuclei on the right. Now, fission reactions produce massive amounts of energy, typically, in the hundreds of mega electron volt energy ranges. That is a lot of energy. If you think about it, just to put things in perspective, we talked about ionization energy last year, the energy it takes to remove an electron from an atom. And the ionization energy of, let's say, hydrogen is somewhere around like 13 electron volts. Okay, so compare 13 electron volts to 200 million electron volts, and you're talking massive, massive, massive amounts of energy. Okay, and again, this is per reaction. If you multiply by, billions and trillions of reactions happening per second, you can get a lot of energy from fission. So this is what a typical fission reaction might look like, and I apologize that the slide animation is kind of messed up so you can't see it very well. Let me take some of this off. What you see is on the left side here, you have uranium-235, and it is bombarded with, that means it is hit by a neutron. Now when that happens, that neutron kind of gets sucked in, and for a very, 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 very small amount of time, it becomes uranium-236. Okay, now uranium-236 is so unstable, it basically starts to split. Imagine like, if you were to let's say you get a water balloon and you were to shoot the water balloon with a BB gun and film it in slow motion. Okay, so right when the BB hits the not watermelon, water balloon. Right when the BB hits the water balloon, if you use your imagination for this part, you can imagine it kind of like rippling and becoming unstable right before it actually pops. That ripply unstable part is the uranium-236, and then a split second later, not even a second later, it's going to split into two daughter nuclei. Here we have xenon-140 and strontium-94, plus here are the additional neutrons. And again, I apologize for the bad formatting. Now, these are not the only possible daughter nuclei that you can get in fission. Fission can produce lots of different types of daughter nuclei, but this is one example of a fission reaction. Now, just to show you a quick animation of what that might look like, here we have a uranium-235 nucleus. You can already see it's kind of wobbly because it's unstable. And when we hit it with a neutron, it becomes 236 for a split second before splitting. Okay, so let's watch that again. Okay, neutron goes in. It's wobbling right now. 236 is so unstable, and then it splits. Here, that yellow bit you can see is the energy being released. These two big pieces are the two daughter nuclei, and here it's actually it's actually 3 neutrons, not 2, that come out. And so whether it's 2 neutrons or 3 neutrons kind of depends on what reaction ends up taking place, and there's no way to predict that beforehand. It's kind of randomized. Okay, so that is basically what nuclear fission would look like. Okay, now just to well, I should do the simulation. I'll show you one more video in just a second. Why is the heavy nucleus splitting when it's hit by a neutron? Okay, so remember, at high enough atomic numbers, you basically end up with a situation where all of the atoms are unstable because they're so big. Remember, in a normal stable nucleus, you have to have like a balance between the strong nuclear force and the Coulomb force, the electrostatic repulsion between the protons. And at some point, there's just so much happening inside the nucleus that there's no way to maintain stability. Okay, and so when you're dealing with fission, you're already dealing with like really big bursting at the same nuclei to begin with, and so this is really like simplification, but if you poke it, so to speak, with a neutron, you're basically going to cause it to split. Again, if you imagine like a water balloon, if you fill up a water balloon right to the point where it's about to pop on its own, and you, let's say, poke it with something, it's going to split. Now, that's a highly simplification. It's definitely more complicated than that, but I don't want to get too far into the weeds as far as the technical details are concerned. Although I should point out that with fission, of course, we talked about this in the last video, but anytime you have a nuclear reaction, the products tend to have a higher binding energy per nucleon than the reactants. And so you would expect, if you were looking at a binding energy per nucleon graph, that the products would be more stable, and therefore would be higher up on the binding energy per nucleon curve. So let's talk about the awesome part of fission, which has to do with what's called a chain reaction. And so the idea is that it is the neutron that causes the initial fission to occur. And so you also have neutrons as a fission product. And so the idea is that if those neutrons can go on to cause more fission on their own, then you can get what's called a chain reaction, something that might look like this. You have one neutron that causes one fission event. That fission event, let's say 2 neutrons or 3 neutrons come out. Those neutrons can also cause more fission events. And so theoretically, you can get this kind of exponential growth going on. And when that happens with the exponential growth, remember, in each of these nuclear reactions, you're releasing a lot of energy. And so this is going to produce, more and more reactions very quickly, and that's going to produce so much energy, and you get a giant explosion. And that's basically the idea behind a nuclear bomb, a fission bomb, is this what's called an uncontrolled chain reaction. Okay, now there is a difference between a controlled and an uncontrolled chain reaction that you probably need to know about. Make sure you can explain the concept of the chain reaction fully. The difference between a controlled and an uncontrolled chain reaction is an uncontrolled chain reaction is what we saw in the last slide. It involves an exponential growth of fission. In other words, one neutron, leads to 2 neutrons, it leads to 4 neutrons, and 8 neutrons, and so on. In a controlled chain reaction, you basically set it up so that you don't get exponential growth. You have one neutron producing one fission, and then 2 neutrons might come out, but only one of those neutrons actually causes more fission. Okay, now normally we'd spend a lot of time talking about how that happens, but in the interest of time, we're going to save that and maybe go into more depth when we get to topic 8. Okay, but for now, let's just say it's good enough to know the difference between a controlled and an uncontrolled chain reaction. Let me just add one more thing, just to make these words more concrete. An uncontrolled chain reaction, okay, you typically see with a nuclear bomb. a controlled chain reaction you have in a power plant. Okay, so power plants don't have uncontrolled chain reactions. At least, hopefully, they don't. Otherwise, that might be bad. But the uncontrolled chain reaction is how we create nuclear weapons, basically. We want that exponential growth because we want a lot of energy to be released very quickly. And again, normally it's been much more time talking about how do we arrange it so these things happen. But in the interest of time, I'm not going to spend too much time going over that. I do want to show you really quickly a short video. Okay, so this is just to show you a nuclear fission chain reaction. And what you're seeing here is each of those neutrons coming out is producing a new fission, and so the whole process increases exponentially. Okay, so some notes about fission. A nuclide which is capable of undergoing fission with a high probability of success is called fissile. Okay, examples of fissile materials would be uranium-235, which is by far the most common nuclide to see in IB questions. Uranium-235, uranium-233, plutonium-239, and plutonium-241. Again, by far the most common one to see on IB questions is uranium-235. You might sometimes see plutonium, but it's not as common. Okay, note what is not an example of a fissile material is uranium-238. Okay, uranium-238 is not fissile. It is theoretically capable of undergoing fission, but it's not very likely. Okay, so typically what happens is uranium-238 absorbs a neutron rather than bursting and causing fission. It actually absorbs a neutron and becomes uranium-239. And actually, uranium-239 is radioactive, and it actually undergoes radioactive decay and turns into neptunium, and neptunium also undergoes radioactive decay and turns into plutonium. And so actually, I guess I should say you can create plutonium by bombarding uranium-238 with neutrons. Now, the reason that's important, I should say, is uranium-235 is fissile. Like I said before, it shows up most often on IB questions. 99% of the uranium on Earth is uranium-238. Okay, so there's actually a very, very, very small amount of 235 available on Earth. And there's different reasons for that, but probably one of the most common reasons is because the half-life of uranium-235 is much shorter than the half-life of uranium-238. And so a lot of the 235 that was, in existence when the Earth was formed billions of years ago has already decayed away. And the half-life of uranium-238 is much, much, much longer. And so that uranium-238 is still around. But again, 235 is fissile and 238 is not. And so typically what we need to do in order to actually make practical use of uranium is we have to have it undergo a process called enrichment. Okay, now enrichment, this is another vocabulary term. Enrichment is a process whereby you increase the percent of fissile material in a sample. Okay, and again, normally I'd spend a lot of time talking about how do we do enrichment, but we don't really have time for that, so I will just say that that the amount of enrichment required for a nuclear bomb is much, much, much higher than that for a nuclear power plant, a nuclear reactor. Because remember, in a nuclear weapon, you want to have that exponential growth chain reaction, and you can only get that if you have a lot of uranium-235. So just something to keep in mind. I guess what I'm saying is it's much harder to make a nuclear weapon than it is to make a nuclear power plant because the enrichment requirements. Okay, and one of the last things we're going to talk about is the effects of nuclear weapons. Obviously, the first nuclear weapon was produced by the United States during World War II as part what's called the Manhattan Project. Dropping of 2 of those weapons during World War II led to the end of that war when we dropped 2 weapons on Japan. Just something to keep in mind when considering the possibility of fission weapons being used in nuclear warfare. Little Boy, which is the name of the fission bomb dropped on Hiroshima, only about 1 to 2% of that uranium actually underwent fission. Okay, because when the bomb started to explode, all the uranium kind of scattered away, and so it was not able to undergo fission. Okay, so keep in mind that only a very small fraction of the total uranium actually underwent fission, and yet still produced that much energy. Also keep in mind that fission weapons, when they explode those daughter nuclei, they can also be radioactive, and so nuclear weapons also release highly radioactive substances into the surrounding air, some of which have very, very long half-lives. We've already talked about how uranium-238 can produce neptunium or plutonium, or the daughter nuclei can also be radioactive. Just a really bad situation all around. If you want a visual representation of how dangerous nuclear weapons can be, you can check out this website. Normally I would show that to you in class, but it's not really possible right now. So I would definitely encourage you to check this out. And then the last thing I want to say is that you might hear this term on the news sometimes, nuclear proliferation. And basically nuclear proliferation is the spread of nuclear technology to countries who don't have this technology. And that's something that a lot of countries are really worried about. And so we spend a lot of time and effort monitoring, enrichment facilities all around the world to see who is trying to get nuclear weapons. And a lot of countries would say that they're trying to get nuclear technology for power purposes. And we, and when I say we, I mean the United States may or may not believe that. Okay, but if you ever see that term nuclear proliferation, that's referring to the spread of nuclear technologies to other countries who don't currently have that technology. Okay, so just really quickly, I want to take a look at 2 examples from y'all's worksheet that have to do with fission. If you want to take a look at what this says, you can. But let's pull up that worksheet. Question number 10 is a very, very easy question as long as you recognize what we've been talking about in this slide. They give you a nuclear reaction, and they basically ask, what type of nuclear reaction is this? Okay, so see if you can figure this one out on your own. Okay, so obviously this whole video has been about fission, so the answer for this is B. You can spot this pretty easily because number 1, you've got neutrons on both sides. Number 2, even though you can have artificial transmutation caused by a neutron, it's not as common. And plus, we have 1 neutron, we have 1 thing on the left side besides the neutron, and then 2 daughter nuclei on the right side. And so you're always going to have 3 products in nuclear fission because you have the 2 daughter nuclei plus the excess neutrons that are produced. Okay, either 2 neutrons or 3 neutrons, typically. Okay, so that is question number 10 on y'all's worksheet. And then just to look at one more, question number 12C says nuclei of uranium-235 bombarded with low energy neutrons can undergo nuclear fission, and they give you the reaction. And it says show using the following data that the kinetic energy of the fission products is about 200 MeV. Now this is a show that question, and it's very important that you realize on a show that question they are basically giving you the answer, and they want you to show that that answer is correct. Okay, in other words, that 200 MeV, we are not meant to use that. We're meant to check the final answer against that. We're supposed to get that as a result of our calculation. Okay, so we're basically trying to show that the energy released in this reaction is about 200 MeV. Now, we've talked about how to do problems like this before, but we have a mass defect. We have more mass on the left side than on the right side, and so we want to start by finding the mass defect, and then recognize that that mass defect corresponds to energy being released. Okay, so first of all, the mass defect would be the mass of the reactants. Okay, so we have 1 neutron, so that would be 1.00867 plus the mass of uranium-235, which is given, 235.04393, minus the mass of the products. We have barium, krypton, and 3 neutrons. Okay, so I'm going to write those masses down as well. And I'm starting to run out of room. We have 3 neutrons. And if we subtract all of this, then we should get a mass defect. And I just did this calculation. Okay, so 1.00867 plus 235.04393, and then subtract the mass on the other side. As you're doing these calculations, keep in mind that there's 3 units for mass, there's only 2 units of energy, and so we are going to need to convert here in just a second. Okay, we get a mass defect of 0.186U. Okay, they want the energy in MeV, and so we need to convert that. Sorry, not MeV. Yeah, they want the energy in MeV, so we need to convert this mass defect from U to MeV per C squared. Remember, MeV per C squared is a unit of mass. Okay, so this conversion factor is given to you in the data booklet, and so if you multiply that by 931.5, you get a mass defect of 173.3 MeV per C squared, and then the last step is to take that 173.3 and multiply by C squared. Okay, now because the unit here is already MeV per C squared, the C squared cancels out, and we get E equals 173.3 MeV. On a show that question, typically the answer you get is going to be different from the one they give you, but if you recognize that there should only be 1 sig fig here, if you take 173.3 and round it to 1 sig fig, that is approximately equal to 200 MeV. Okay, now on a show that question, it's very important that you understand that the person grading is not looking for the 200 MeV. They gave you that already. They're looking for the next to last step, that 173.3 MeV, because that's the one that tells them, hey, this person knows what they're doing with the calculation. Okay, so your last step on a show that question should always be to round from your answer to the answer that they give you to check. Okay, so that is a fission question, and more generally, that is a mass defect energy release type of question that we've seen before. Okay, so hopefully you have a better sense for nuclear fission after watching this video. I definitely encourage you to do more research on your own and check out the videos I included, or I will include in just a moment. As always, please let me know if you have any questions, and I will see you guys in the next video.